Last class, that is the first class on electromagnetic induction, we have learned that when the flux linked with a closed circuit changes with time, then the EMF is induced, and the induced EMF is governed by minus d phi dt. Then we distinguish between the motional and transformer EMF. Firstly, if we consider a circuit which is at rest and is placed in a time varying magnetic field, then the EMF that is induced in the closed circuit is known as transformer EMF. On the other hand, when a moving circuit passes through a static magnetic field, it gives rise to the motional EMF. And when a circuit moves in a time dependent field, both the motional and transformer EMF comes into action. We said that EMF, that is the the transformer EMF is governed by minus del B del T ds integrated over all surface. This is the transformer EMF, and on the other hand, this integration is over the surface bounded by the contour C of the closed conductor. And on the other hand, whenever the circuit moves with a velocity v in a magnetic field which may have space variation but doesn't have any time dependence, then the motional EMF is this, and when both of them are operating, we must add these to get the induced EMF. But this relation is valid in all the three cases, so it will be better to use this expression all alone. Here I will consider an example which will distinguish between the three cases. First, the basic thing is that I have a coordinate axis like this, and there are two rails which are parallel to y-axis. One is along y-axis, another parallel to y-axis. This is a conductor. So, and we have a conducting material which can slide over these rails in this direction. So whenever its velocity, we are talking about its velocity, the velocity is along positive y direction, and in the x direction it extends. This rail are separated by a length L. So this can be written as J cap times its magnitude, and a magnetic field that acts is along z axis. So first case is that the rail is fixed at a length, say B. It is fixed at a length B, and case 1, this is PQ. PQ is fixed. PQ is fixed at y is equal to B, and magnetic field B is K cap 4 cos of 10 to the power 60 and millitesla. I have taken this problem from the book of Sadiku. So since it is the conductor is fixed, the closed conductor is P, O, P, Q, and let me call it R. So this is the closed loop. And one must consider the transformer EMF. So the transformer EMF is area, the flux phi linked is equal to area, which is L times B times B itself, This is the flux, and if we differentiate it with respect to t, we will get the transformer EMF. EMF is simply minus this indicates a back EMF. Second situation, we consider the B is to be fixed and PQ is moving with a velocity V. V is equal to say 20 meter per second along J cap, and B is fixed at 4 millitesla. In that case, we should consider the motional EMF. The motional EMF developed is V cross B dot dr. This is the motional EMF. Since it is along J cap, it is along K cap, so this part is J cross K, so this is equal to along I cap, and this, so dr along this direction, it is along I cap. This is also along I cap, but this this is J along J cap and this is along J cap, which does not contribute. So the contribution comes from the parallel sides only, and it gives you the motional EMF. Only you need to consider the component of R cap, which is parallel to I cap. And third situation is that the PQ is moving with velocity, say again 20 meter per second, and B is again in millitesla. In this case, you see that the rail is moving, or this conducting rod is moving, and the magnetic field is also time dependent. So it is the most general case, and when both of these two will be operative, and the flux can be obtained. Flux linked d phi is this much is fixed and this is variable, so the flux is obtained by dx dy times b. This is this is 4 this result will be come out as a function of t and y, and now whenever we differentiate this with respect to time, d phi dt, two part will come. One is this part and another part is dy dt. Dy dt is actually the velocity, that is 20 meter per second. So we are to put this and finally get the EMF. So I think this example is a very nice one, and once again I repeat, I have taken this example from the book of Sadiku, which is also is referred in your syllabus. Now I shall consider few more examples. Firstly, I consider a long state wave carrying a current I, steady current I, and a conducting rod. So So let me describe the situation. This is a long straight wire which carries the current I, and we have a rod which is moving in this direction. Now this end is at a distance A and this end is at a distance B. So the nearer end of the rod is at a distance A from the current carrying conductor, straight current carrying conductor, and the far end is at a distance B. As this is moving in this direction with velocity v, after time t dt, this will move a bit. So this will be the position of the rod. So this is the position of the rod at time t, and this is the position of the rod at t plus dt. So if we consider this much, then this length is vdt and this much is x, dx. So the field, if we consider the field at a distance x due to a straight wire, the field at a distance, this distance is x, then this is mu 0 I upon 2 pi x. This is the field, and the flux linked with this is d phi is equal to this multiplied by this is the area dx times dt, and then it has to be integrated over dx. So the flux linked with it, so d2 phi is equal to b dx v dt. So this is the flux linked with this much. Now if we integrate this expression, so this is mu 0 I upon 2 pi dx x v dt. So the flux linked with the entire rod, this is integration over x. So this is mu 0 I v 2 pi dt, and this is a to b dx x. So this is log. So this becomes mu 0 I v 2 pi dt log b by a. Now, so d phi induced EMF is equal to d phi dt This is the induced EMF. As a second example, we consider a rectangular closed loop placed in xy plane with its sides parallel to x and y axis, and a magnetic field. There is a straight current carrying conductor which carries a current, and we have a rectangular loop. This much is B, this much is A, this is O, and this is at a distance A away from the there. So what is the flux linked with it? We have to calculate this one. What is? Firstly, we consider a strip at a with dx. So the field at a distance x, if this is with the x, again the field is mu 0 I by 2 pi x is the field at there, and the flux linked with this is d phi is equal to, we have to integrate this much dx dy, so this is b dx dy integrated over x and y. So when we integrate over y, we get L, so mu 0 I L by 2 pi, and then dx upon x. X integration limit is from a to a plus b. So this is equal to mu 0 I L upon 2 pi log of a plus b by a. Since this ring is fixed, the flux will depend on time only if I has a time dependence. That is, if the current is a steady current, the flux is linked with the loop, but no EMF will be generated. The induced EMF is mu 0 L upon 2 pi only the time dependent part. If this is non-zero, EMF will be induced, otherwise no EMF will be induced. Another type of problem is that the phi is already given as a function of time. So if you give the flux, say flux linked with its circuit is given by pi as a function of time, phi as a function of t, say a t cube b t square c t plus d. It is given in wavers. Then if you differentiate it, we will get the EMF as a function of, we can get the induced EMF. Another type of example that I am considering is a disk, conducting disk placed in xy plane. So this is a conducting disk of radius r. Radius r is placed in xy plane. This is the z-axis, and the ring rotates with constant angular speed omega about the z-axis, and it is being placed in a magnetic field which is also along the axis of the ring. So the problem is, we have a ring of radius, circular ring of radius, circular disk of radius r, and it is rotating about its axis, which is the z-axis in this case, and the magnetic field parallel to its axis has been applied. So what is the flux linked to it? Say at time t, we consider this part. This is radius, which after a time dt moves to this, where d theta is this, and d theta is equal to omega dt, because it is moving with the angular speed omega. And the area that is being traced out by this area part is ds is equal to r dr d theta, and this area element is along the z-axis, so the flux linked with it d phi is equal to b ds. B dot h is actually b dot ds, where b and ds are in the same direction. So this is b r dr d theta. and d theta is equal to omega dt. So this is a double differential, so we write this, and so the flux linked with the entire disk is obtained by integrating this much over, so this is b omega, a constant taken out, dt r dr from 0 to capital R. So this is half b omega r squared dt. This is the flux linked with the circuit during time t. So EMF is, magnitude of the EMF is d phi dt. So this is equal to half b omega r square. If we write it in terms of nu, so omega is equal to 2 pi on times nu, or f, whatever you call it. So this will cancel out. R square. Another interesting, the same problem can be tackled in another way. We may consider a rod of length capital R, a rod of length capital R, and the rod is being rotated in a plane, keeping one end fixed. Then it's the problem ultimately reduces to this one, where R is replaced by the length of the rod, and omega is the angular velocity of the rod with which it is being rotated in a plane. Another example, or rather the last example of this category that I am going to consider is that a rectangular loop is being placed in a magnetic field, and the loop is pulled to take it out of the magnetic field. So we consider a region, say this is the region in which the magnetic field B is directed into the plane of the board, and we have a rectangular loop, and our aim is to drag it out. We want to drag it out, so what will be the direction of the EMF? Say at time t, this much is the length of the loop which lies within the magnetic field. So by assumption B is 0 outside this region. So within this, the flux linked, if this is B, then the flux linked with it is Bx capital B, because this area is towards me, this area is and this is the flux. So d phi dt is equal to B VB, where V is the velocity with which the ring is being pulled out of the loop. So this is the EMF induced, and this EMF, the EMF will try to reduce and this EMF will give rise to a current, and a current will be induced in this circuit, and the current will try to decrease the magnetic field. So that will describe the direction of the induced field. If we apply Gauss-Seidel law, it will be found that the current is flowing in this direction. That is, this induced current will be in such a direction that the magnetic field is towards you. That is, the B induced will be towards the reader. that will fix up the direction of the induced field. So this much on the problems of electromagnetic induction. In the next class we shall consider self and mutual inductances.